Hello again, and welcome to This Old Balls Up, or whatever it's called. I can't remember. So today we're going to get back to the Model Engineer beam engine, which I'm very happy about. And today what we're going to do is make this thing. Now I'll tell you what that is and give you a little bit of background about it in a couple of minutes. First of all, I got a couple of things to say, a couple of announcements to make very quickly. First of all, I want to thank my friend Jim at Jim's Workshop. Please go and check out his channel. Back in February, actually, he stopped by and gave me, he's gifted me a number of things, actually. He's a very generous person, very, very generous. I traveled with him to the Indiana Engine Show last year, and that was just a great time. Anyway, he gave me this 3-inch face mill, and I've obtained some good inserts for that, and I'm going to be putting that to use, so I look forward to that. Next up, I received a channel sticker. Haven't had one for a while because I've sort of been on hiatus a bit, but Tea and Biscuits reached out to me, and he sent me one of his stickers. Now you should go and check out Tea and Biscuits. He's a lot of fun. Into amateur fabrication. He's building his own car, very prisoner-esque car, and has a scale model Burrell steam engine, steam traction engine specifically, which is phenomenal, and hopefully one day I can get to see that at one of the UK steam shows. I try and stop in at those now and again when I go back and visit. Anyway, Tea and Biscuits, excellent channel. All kinds of model steam engine stuff going on there, model engine stuff. I recommend you go and check that out. Link to his channel will be below. Okay, moving on. A short while ago I mentioned the Indiana Engine Show, and it's time to start thinking about that and getting prepared. My friend Aaron has sent me some flyers, and I shall put a link to the website for the Indiana Engine Show below. This is a great show. I went last year, had a thoroughly excellent time. The only thing I regret about last year's show is that I didn't actually take an engine to show. But this year I will. That's on October 4th and 5th, 2025 at the National Auto and Truck Museum in Auburn, Indiana. A really great location, great venue, and it's going to be a lot of fun. So I hope a lot of you will go. I will be making mention of this throughout the rest of the year. Now, one more thing briefly before we get into the actual machining content is a gift I had from my friend Aaron at the Indiana Model Engine Show, and he sent me this Christmas ornament, which I think is pretty funny. I got a real kick out of that when I opened that up today. So thank you, Aaron. Thank you very much for thinking of me when you were on your vacation trip. So I'm going to find a spot in the shop for that. I'm not going to wait till Christmas. I'm just going to have it up all the time. Okay, remember, if you'd like a channel sticker, please just write to me at this email address and I'll send you one. You don't have to have a YouTube channel. If you just want one for your toolbox or to put on the mirror of your bathroom or whatever, then just shoot me a note and I'll send you one wherever you are in the world. All right, what say we do some machining? Right, got the part set up in the mill, ready for drilling the various holes. Got the drawing up on the screen there, so it's easy to see. So what is this thing? Well, on the plans that come with the engine kit, it's called a plug. Now I'm doing this slightly differently to what's on the plans, and the reason for that is because I've made an alteration to the base casting, and you can see what I've done is I've machined off the boss and the two rails that were in this area. The casting is such that those are just way out of position, and they would still work, but left as they were, they would be visually unappealing. The boss for the cylinder is way off center, and it would be very obvious once it's all assembled with concentric components sitting on top of a boss that's out of concentricity to them. It just wouldn't look very nice. And I had some feedback from Mitch, who's a writer at Model Engineer magazine, who said, yeah, you might want to deal with that now because everybody gets fed up with that and they all end up coming back and machining it off and making a disc to go in there. But since I am forewarned, I've decided to incorporate the disc into the plug. Now, the traditional set comes with a piece of a casting for this item. That was not included in my kit, and it wasn't supposed to be. It was not in the list of parts. And that's just fine because I've decided to make one out of hot rolled steel that I had laying around. And so I've decided to include that boss feature in this part, as you can see. The reason this surface is sloped is because this goes inside the cylinder, and at this lowest point there's a drain cock on the cylinder for draining water out after running. So this is just a sloped surface. So if you're going to make one of these engines and just run it on air, you don't even need this slope. You could just make this a flat surface and it would run perfectly well. Or with steam, come to that. It's just that with steam you have to deal with the condensate. But I've decided to just make this as accurately as I possibly could, and that means not scribing lines and machining to a scribe line, but trying to set the angle accurately by using a sine bar, and then by finding location in space by using a tooling ball, which was just an interesting exercise for me. So let's get into that. Would you like me to go through the shop mathematics that go into that?
I have a bad feeling about this.
But it's kind of fundamental to how to do this and to calculate positions without resorting to CAD. Now that said, I've drawn it all up in CAD just because my scrawl is difficult to read. But let's go through the maths. Here we are in SolidWorks, and this is a model of the component and the fixture with the tooling ball. This is how it looks from the side. And so what am I trying to do here? What we're trying to do is cut this face and keep it oriented to the bolt pattern, because that is going to get the lowest point of the slope to where the drain cock is, so you can get most of the water out when you drain the cylinder. Now obviously we will set the part up in a vise on this fixture, but since I have a simple manual mill, I'm not going to come and do this by moving the quill up and down, so we will set it up like this, and we'll use a sine bar to get the angle accurate. And then what we can do is use this tooling ball as a reference, and because it's round, we're not influenced by a fake sharp corner, and we can touch off on that, having calculated the distance from the top of that ball to this surface. Now sometimes what people are tempted to do is machine a component like this to this height and leave this piece of material in place and then try and reference this corner, which would work fine for this because this is not actually a critical component. I'm just trying to make this accurately for the practice. But if it was a critical component and the geometry was really important, you could very easily run into trouble because corners are never truly sharp and you wouldn't know exactly where you were if you were just trying to touch off on that. You could be slightly off one way, either down this side or along the top. The corner could be broken to some amount that you don't know. So it's not an accurate way of making components. That's the advantage of a tooling ball, where no matter how you orient this, you've got a known surface in space to come off of, and it's not influenced by a non-existent sharp corner because we're just using a perfectly round sphere, or as near as you can get it. Hope that makes sense. So the trickiest thing in this situation is actually just to figure out where the triangles are. So the first thing to do is sketch it out one way or another, and by hand is perfectly good. It's how I actually did this. This drawing is just to help explain the calculations. So let's get into that. This is the area we're interested in, and here's the crux of the matter. We're trying to establish this dimension from this finished face to the surface of the tooling ball. Again, here are all the dimensions that we know, and so what we have to do is just figure out where are the triangles and what do we know and what don't we know. And if we zoom in here, you can see it start to take shape. So there's the line showing the distance we want to know. We know this distance, that's 1/4 inch, because that's the radius of the tooling ball. So that means we have to figure out this distance. So the missing piece of information is this distance. And to get that, we just have to work backwards and figure out what we do and don't know. So we've got our triangle here, and we've got the triangle here. So we can work out that we need this dimension B. In order to get that, we need to work out this length. Now we know that's 1/8 inch. Which just comes from the height of the tooling ball from the surface and the height of the part from the surface. So that's a known dimension. What we don't know is this bit. But we can get that from this triangle because we know this dimension. This dimension is the outside of the part to the center of the tooling ball. So now we can start working our way back through it. Having figured out that dimension, we can use trigonometry to get dimension A. That's that equation. And knowing now what dimension A is, we can get dimension B because we know it's 1/8 of an inch minus A. So that's that calculation. Now we know this length of this little triangle, which I've drawn here. So now we can calculate C. C is B times the cosine of this angle, which is the same angle that we worked out right at the start, 5.572. That comes from the dimensions of the finished part. That's this calculation. And now knowing that, we know this dimension is 1/4 of an inch because that's the radius of the tooling ball. Simply add the two together and there's the D dimension. So if we touch off on the tooling ball, that establishes the height of the end mill, and then we start machining and bring the knee up or the quill down depending on how your mill is set up, that dimension, and we end up machining this face. Very straightforward. There's another way of doing it, by which I mean the calculations, because the triangles are all the same shape with the same angle. You can use ratios. So we know a lot of information about this triangle. We know everything about that. And this one is simply a ratio of it. So you can calculate the ratio of this length, which is 1.2813, to this length, which again we know, and that gives you this ratio, and then you can simply use that to extrapolate dimension A and therefore get dimension B. So there's two ways of doing it, and basically it's just a matter of understanding what your geometry is, and then the calculations become very simple. There's really, in machining, trigonometry is kind of the #1 mathematics that you're going to encounter, and that's why I learned these formulas a long time ago when I was at school with this mnemonic. Some old hag cracked all her teeth on apples. Sine of the angle is the opposite over the hypotenuse, and it's just the first letters, and it just helps you remember it. Anyway, that's how I established this dimension to come down and do the machining from. Right, so off camera I made the fixture to hold the partly machined part, and I haven't filmed that just to save a little bit of time, because honestly it's this chunk of leftover scraptonium, which is actually 6061 aluminium, aluminized aluminium. And what I've done is I set that up on parallels and then decked off the top to get it nice and flat, and then machined in the bolt pattern in exactly the same way as I machined the bolt pattern into the actual part. And then I added a reamed hole in the center, which is for an alignment pin, and a reamed hole out in this position, and that's for the gauge ball. So this is a gauge ball. These come in various different sizes and types. This one's an all-in-one piece. You can also get these as a ball lightly tack welded onto a post, and the idea being that that's a deliberate fail point in case you crash into it. I think it's highly likely I'll crash into it, so I got a solid one. Basically, so I've still got it up. I'm not planning to crash into it. But they also come as a slip fit and a press fit. So these come as press fit as permanent installations. But this one is a slip fit, so that I can use it again and again. And so it's a very close fit in the reamed hole. And now I can touch off on that, and I know accurately where the end of the tool is in relation to the top of this surface. And I can trig out and calculate where I need to be. If I needed to, I could also touch off on other surfaces if I needed to get to other points in space. As it happens this time, all I have to do is angle this get the height right, and then machine away the material on the part. So that's some more waffle around the tooling. Now let's have a look at it in service. All right, here's the setup. Got the sine bar set up. There are the 3 blocks, spacing it accurately. There's our fixture block with the part and the tooling ball. So the next stage is to come and touch off on the tooling ball using the end mill, but we'll touch off with a feeler gauge, and then we'll know the height of the end mill, and then we can bring the knee up the appropriate dimension and just start skimming that off. And we'll just take light cuts just because this is the first time I've done it. Okay. I now know that I'm 0.04 millimeters away from the top of the ball. And as you know, that is 1.5 thou. Now I'll come over here and I'll lift the knee up 1.5 thou. And I now know I am basically at the top of the ball. Now all I have to do is cut away and raise the knee up until I get 3152 on here. So that's going to be quite a lot of material to take off, but that's alright. And so on we go. Well, there it is. That wraps it up for this one. May seem like an over-the-top approach to make a component like this, but I think it's worth thinking through those kinds of setups and understanding the geometry, because I think it just improves overall understanding of machining and spatial relationships and all of that good stuff. So, you know, yes, there's other ways of doing these things, and we can all pick whatever route we choose to make our model engines, right? It's up to us. as with everything, ask 10 different people to make something and you'll get 10 different methods. There's no wrong way as such. This is just, I just wanted to provide a demonstration of a kind of tool and die approach that I enjoy trying to take in order to make these things. It's just very satisfying. So hope that you enjoyed that. Don't know if the waffly stuff about the geometry and the trigonometry was of interest. So if it is or it isn't, feel free to say so in the comments. If no one really enjoys that, then I won't do that in the future. But I thought I'd throw it in there as something different because it is valid and it is a part of the setup, and it helps demonstrate how these things can be done without expensive computer systems. That said, there's plenty of free or a couple of good free CAD options around. Check out Onshape. That's apparently very good. I use SolidWorks because I have it professionally, so it's handy to have. But I nevertheless like to work through the maths. So hope that was somewhat enjoyable. As always, may your dimensions be in tolerance and your surface finishes chatter-free. Be seeing you.